So so you asked what I did. So I did go out of town, and don't know what that is. I guess that's the title slide. We ran a meeting on geothermal energy from sedimentary basins to look at the challenges, right? So there's a huge amount of heat locked in sedimentary basins. The same way, I'm not sure what majors you are in, whether it's energy engineering or petroleum, or actually any of the other majors for that matter. And so there is some thought that you could actually harvest some of this heat, maybe in petroleum reservoirs when you produce oil, that you also harvest the heat that comes out with that, because as you know from one of our examples that we did, the geothermal gradient is about 25 degrees centigrade per kilometer. So if you go down a couple of kilometers, so Marcellus is at about 9,000 feet, so that's basically 3 kilometers. 10,000 feet would be 3 kilometers. So it should be 3 times 25 plus surface temperature, which is 20 degrees centigrade. So that should be close to 100 degrees C at that depth. A little less, maybe 80. And so if the fluids that you produce, the gas or the liquids from Marcellus you produced with and took the heat out of them, then you could scavenge that. That's not very useful for Marcellus because it's so tight that you don't get much flow rate volume. And the amount of heat you get is going to be the product of the temperature change, the mass flow rate in kilograms per second, and the specific heat of that fluid. If it's water, you know that it's 4.2 kilojoules per kilogram per degree C, right? So specific heat capacity of the fluid, the temperature change that you've produced it at, and also the mass flow rate. Kind of makes sense. And you can work that out. The product of those three should be in watts. And so you'd like to be able to get large flow through these sedimentary basins. You'd like to be able to either inject water and sweep it, and for it to come out. And so this is a way of engineering it, which is different from current geothermal projects. And so on the Wednesday, yeah, you can hand it around until we finish off today. Yeah, hand it around until we finish today. And so on the Wednesday, we went out to some places down the Basin Range. So the Basin Range, so if you look at this continent, the western part of the continent, California, is a stalled subduction zone. So you have a plate going underneath California that makes the Cascade Mountains, Cascades in northern western part of the U.S. San Andreas is this locked portion of the fault, which the plate boundary going underneath has stopped, and now it's a strike-slip fault. And in response to that, the whole west of the U.S. is in kind of extension. It's being pulled apart very slowly. And as a result of this extension, the Basin Range is formed. So if you go out west, you'll see that kind of on a north-south axis, all the ridges are aligned north to south. They're being pulled apart to make valleys as these blocks drop down. And so as a result of that, it's actually quite conducive to geothermal power. One, because it's hot, because it's a former subduction zone. And the second one, it's being pulled apart, and so it means it has some permeability to be able to push fluids through the system either naturally or unnaturally. Yeah, I'll grab it. Thank you. And so this is a trip to basically a place that was halfway between, hence this map here, halfway between Salt Lake City and Vegas. So if you have some appreciation of the geography of the western U.S., I guess, see if this is working. Yeah, so Salt Lake City, Vegas, San Andreas here. This whole region has these north-south ridges, just actually a bit like the ridges here, but for a different reason, which is being pulled apart. And it's quite hot. If you look at a heat map of the U.S., all the heat is in the west, where none of the population is, which is a bit of an anomaly. And so we went down to a couple of existing geothermal power plants, halfway between, as I say, to Vegas. So St. George is a place that in the 1950s, just east of the Nevada test site, where there are a whole bunch of cancers related to airborne particulates from atmospheric testing of nuclear weapons, just drifted eastwards with the jet stream. And Salt Lake City, this is Highway 15, I guess, comes down here. So we were down here in a couple of plants. So let's have a look at what we got. So I guess How much do these plants make? Not very much, about 25 to 50 megawatts. And so, but it's interesting because, so right here, this is, I forget the name. I wasn't obviously paying enough attention. I guess we don't, I don't know. You're asking the wrong person. Oh, we don't want music on here. How do we get the music off? You won't be able to hear me. Where? Oh, yeah. Yeah, I tried. Yeah, okay. This one you mean? But it doesn't do anything. Oh no, infinite loop. I tried doing that last night. Aha! Aha! It was actually very nice music. So this is somewhere, yeah, don't leave after you signed that. And so the irony of it is, well, not irony, there's a 250 megawatt wind farm right there, which is right next door to it. And as you drive past it, they're absolutely static. And so we were there at noon, it was still static. As we left in the afternoon at 2 o'clock, all of a sudden it was, the rotors were starting to move. So although it's a 250 megawatt wind farm here, the availability is probably less than 25%. It blows in the afternoon. And so I thought that was kind of curious. Obviously, geothermal is baseload power. And so let's go back and see if I can go back to this. So we're going to start up again. I guess that's when. So yeah, so this is just the plant. It sits right next door to maybe 100, 2.5 megawatt turbines. This is the steam plant. You put binary, you put the steam through this and take the heat out of it and then run it through a generator. It's all very clean. I think the noise that's in the background, I don't know why I didn't show that. These are the pipes that go to the wellheads that bring the hot water in. They have these kinks in them so they can thermally expand and not break. This is there's a well over here that's releasing steam, blowing the steam off. It's a binary plant, so they take the hot steam, they put it through these condensers to turn it back into water, so some of it can be re-injected at the same time running it through a turbine. I guess the indoor pictures didn't turn out. And this is the flash plant. So this is where you put the steam in contact with something like isopropanol, which has maybe a boiling point of 35 centigrade. It flashes to steam even less than the boiling point of water. And in a closed system, it flashes to steam by evaporating, runs through a turbine, generates electricity, and then is condensed back above 50 degrees centigrade, and then becomes a fluid. So in other words, you can actually get a steam out of water below 100 degrees centigrade because you're transferring the heat to another fluid, which is able to boil at 36 degrees centigrade. So we went to two different plants, and we scooped through the second one, and I'll go back. And so the first one is right next door to a wind farm, which I think is interesting. 250 megawatts versus 30 or so megawatts. Availability of the wind is probably 25%. I would say that would be, at best, it's 25%, because when you're there, it was just starting to ramp up, and I guess it's going to go through again. And so, just interesting to have these things close together. So, a steam plant, I guess it's not showing the stuff on the inside. Just, if I can do this. Come on, it's too slow. What it's not showing is this. I guess I could just go back into library, right? No, it doesn't want to show those, so I'm not going to worry. It's very clean. So there's this, and the well pad. This is the steam plant. The high quality steam goes through, which has the most heat capacity. This is the binary plant, which uses a closed system of isopropanol to be able to evaporate and run through a turbine. And so, yeah, so you have the brine, hot brine going in here. It never contacts the isopropanol, but in this container here, it's a sinuous path, so there's lots of heat surface area between the pipes. And the stuff outside it is this isopropanol. It transfers all the heat to that. That flashes and then runs through a turbine. And then if you see all these actually you can't see it very well. If you see all these little pots here, these all have impellers in them, which are sucking air through them to be able to move air through the system, to be able to cool off the evaporated fluid, which is in a closed system, so it now is a liquid, and then it can go back through the circuit and then be re-evaporated by the heat from the geothermal reservoir. And so that's how you get heat or electricity out of a turbine when it's running less than 100 degrees centigrade, which is what the brine is. The brine is probably hotter than 100 degrees centigrade. And this is one that was just being built, probably 30 miles away. And so this is just the geothermal piping with insulation going around it. And you can see this stuff moving across the landscape. Again, about 50 megawatts. This is exactly the same plant for the flash plant. So the fluid that runs through this is some heat transfer fluid, which has a low boiling point, is completely closed and is not lost to the atmosphere, but is used to be able to take heat, sub 100 degrees centigrade heat, and actually flash a fluid to be able to run it through a turbine, such as we've been dealing this last. So you can see this is all brand new. So apparently, if they get this plant finished by the end of the year, which is their deadline, then they get 30% of the capital costs back from the federal government, I guess, as a tax incentive. So they've drilled a whole bunch of new wells on an existing site that used to be a sulfur mine, has sulfuric acid coming out of the ground naturally at this place. And this is just one of the wellheads with the attachments that would go to all the other machinery in the plant. And so this is a power supply that goes down to the bottom of the well, maybe at 6,000 feet, it's 2 kilometers, for a submersible pump that actually pumps up the fluid into the upper piping system, and then it goes somewhere to the plants. So this is where it is. Cove Fort, Utah is the location. So that was it. So yeah, so I had a very nice time. Thank you. Hope you had an equally pleasant time. Okay, so is it going to close? So I'm not sure whether people looked at the materials that I'm sure some of you did. I'm sure you guys did, since you're voting with your feet here. Don't know if I want that. Don't know why this. I guess it's thinking about closing. So what I wanted to do today was just summarize the things that maybe were in those two components, 9.1 and 9.2, and then take it the next part. And so you'd have gathered, I think, from that material that dimensional analysis, which is kind of a misnomer really, because you're trying to make them into non-dimensional numbers, but dimensional analysis is an incredibly powerful tool that allows you to say something about the behavior of fluid mechanics systems without ever really writing an equation or deriving a differential equation. It allows you to be able to do experiments, and by judiciously choosing those experiments to be able to scale those up in some way. And so what I want to do is just kind of summarize that in terms of what you've done already, which is in terms of Buckingham pi and the three major non-dimensional numbers that we've talked about, really two so far, Euler number and Reynolds number, and then kind of finish off things about how you might use this in a practical way. So that was the plan for today. So I guess I was going to start with this. And so you went through an example. I think the example was this NOVA program about digging a raptor out of the ground as a fossil, and then seeing whether it could actually fly, the first flying bird or so. And you saw they dealt with it by putting it in a wind tunnel. And the example that we used was all about that. And so the procedure is pretty straightforward. You make a scale model. You put it in a wind tunnel, and you measure the performance. So measuring the performance is you measure the property you'd like to understand. So it could be that you are measuring, say, the pressure at the stagnation point on the front of the wing, if you wanted to do it, or if it's a submarine, maybe you'd be measuring the pressure you have on the nose of that submarine or a ship, because it would tell you something about the force or the work you'd have to do to push it through water. Or for the Raptor case, you might set it up so you can measure the lift force, just measure how much the weight of the Raptor changes as you flow air past it, and that gives you some idea of the amount of lift that you have attached to it. And what you'd like to do is three things. One is you'd like to have a scale model So a scale model in the terminology of fluid mechanics is geometric similitude. So in other words, each dimension, the ratios of all the dimensions, the height of the wing, the web of the wing, and the width of the wing, the ratios of all those lengths is the same. So it's just a scale model. You'd like to have it so that it has the same, do they call it kinematic or dynamic? Let's see in this. Kinematic. So you'd like it to have the same kinematic properties. So let's go to this. You'd like it to have the same kinematic properties. And so for us, that means that the flow regime around it is the same in the model as it is in the true real-life system. And so usually for us, that means saying something about the Reynolds number. So the Reynolds number should be the same. And finally, you use it to be able to measure something that you want to know at the prototype scale. So that's kind of the way that we want to do it. So let me write those things down rather than talking about it. So dimensional analysis. So we're going to pull this all together. So process, I guess. So the basic process is that you have, let's use the wing again, just because it's convenient. So can I draw a wing? Let's see, draw it the other way around for one time. So we have a model, it's not supposed to be a fish. And around that model we want to have some flow regime. And we have a prototype, which would be the same shape. And for instance, we haven't really talked about it yet, but maybe we want to calculate the lift which is on here. And we use prototype and model, so superscripts. It's not so useful to use superscripts when we have a v squared term, which is also a superscript, but that's really what we're dealing with. And so the basic idea is that we could write out, we for instance know that the pressure multiplied by an area is going to equal a force, a lift force. And so if we want to calculate what this lift force is, one way to do it would be to measure the lift, but the fundamental property in terms of our understanding of behavior is going to be a pressure that's applied which is perhaps larger on the bottom of the wing than on the top, and that net difference in pressure is what makes airplanes fly, and you certainly know that. And so what we do is, rather than writing any expression whatsoever, we define the problem in terms of the variables. And so what we could do, and what we did do, is we define all the variables. So the pressure that we have in the system is a function of some particular variables. You know what the variable, well, what are the variables? Well, there's a density of a fluid that's flowing past it. This would be the velocity of the model, right? And the velocity of the prototype. So there's a density, there's a viscosity, there's a velocity, for instance. What else is there? There's gravity, but let's not necessarily worry about that. There would be some dimensions. So we had a length of the wing, which I think we called L, and we had a diameter of the wing, not diameter, span of the wing. So we have length and diameter. And so that's all we know about the system. We don't have any, we do have differential equations to describe it, but we're not going to worry about that. So we know from Buckingham pi that the number of dimensionless terms for the system is So pi terms equals, what is it? It's number of dimensions, number of quantities, I guess. So number of these terms. So we have 1, 2, 3, 4, 5, 6. Number of terms describing system. And we can have as many of these as you want, but the problem is minus number of mass, length, and time represented. So if we know the number of terms describing the system, we have pressure, density, viscosity, velocity, length, and span. So that's 1, 2, 3, 4, 5, 6 in this particular case. And if we look at density, density is equal to mass per volume. Velocity is equal to length time. Inverse, all right. Mass per unit volume, length per unit time. So we have mass, length, and time represented in these. So we have 3 of these. We have all mass, length, and time represented. So by definition, we have a total of 3 terms. So that's the number of pi terms. And so we can go through Buckingham pi to do that. And there was an example in 9.2 doing exactly that. And that's one way that we could go about it. So we know that for this system we're going to have 3 terms. But let's try and cut a little bit to the chase and think about it without doing that. And it turns out that for most fluid mechanics problems, you can describe the behavior in terms of the important variables, non-dimensional variables, tend to repeat themselves. So the first observation is that to be able to do the needs for similitude. So in other words, what you need to have in place so that you can use the information from a model to be able to say something about the prototype. First of all, you need to have a geometric similitude. Which is just a fancy way of saying that if you're going to make a model of a plane to put in a wind tunnel, it should actually look like the plane, just shrunk down to whatever scale you want it. So if you shrink the wing down by tenfold, then it should be 10 times thinner. The web of the wing should be 10 times less. The span of the wing should be 10 times less. And so I suppose that's saying that in our particular case, the length to span of our model is exactly the same as the length to the span of our prototype. So this P is just it's not an exponent, it's just the magnitude. So that's just saying that everything, if you're going to use a scale model, it should be a scale model. It's saying nothing more than that. The second point is you want to have kinematic similitude. I don't know if I should check that that's actually what the second one is. Yeah, kinematic similitude. And so that's physically saying that if you, for instance, if you have your wing that looks like this, actually, let's look. So we made the point, if you looked at the materials before, this is the important figure. And that is that if you take a snapshot at a particular Reynolds number, so Reynolds number is the key here, that the flow pattern around this thing will look like this. So you have these little vortices, these little eddies forming here. There's one here that's been shed, actually there's an eddy here that's been shed earliest. There's one that's been shed more recently, and there's one that's been shed even more recently. This is all going to just move downstream. So the flow system that you have around this rod or sphere, I guess it's a cylinder in this particular case, has this form at this particular Reynolds number. If we looked at a really low flow velocity, then the flow pattern, instead of looking like this, would be flowing to here, stagnation point, hugging around the outside of this cylinder, coming back to this kind of separation point, and then going downstream and off the other side. So a very low Reynolds number, the flow would look like that. At much higher Reynolds number, the flows look like this. At even higher Reynolds numbers, it'll look slightly different. And so it turns out that the index that we use to scale the kinematics, what the flow field looks like, is typically this, just the Reynolds number. And so kinematic similitude really just means that we want to make the Reynolds number of the prototype, or the model rather, Reynolds number of the model equal to the Reynolds number of the prototype. And so that physically means that the flow pattern around the model is exactly the same as the flow pattern we'd have around the real-life prototype. And therefore we have a fighting chance of, if we make measurements of other parameters, that they'll be representative in some way. And so those are the first two of the three requirements. And then the third one is, so if you have a model that's the scale model, if you run it at the same velocity, so by definition you'll remember that Reynolds number is a velocity, a density, a length scale, and a viscosity. So it's the ratio of what? Inertial forces to viscous forces. That's all it is. Turns out to be those units. And this is some length, it could be the wingspan as well. It's some characteristic length. And of course, if the wingspan is scaled in the same ratio, it doesn't really matter what the unit is that you do. It's just that when you measure things on your model, the parameter that you'd use to measure the Reynolds number would be the same on the model and the prototype. So it could, and you'd like it to be a relevant number. And so actually, you could imagine that in our model, the other thing that we have, right, in addition to the shape of the model, which I'm not drawing very well here, that looks like this, we said that we have a length, we have a span, we also have another characteristic dimension as well, right, which we haven't said, width. And so if you're looking at width, typically you'd think that the lift would be related to the planiform area of the wing, not really the thickness. You could probably make it thicker or thinner, but with the same geometric attributes of the shape of it, and the thickness wouldn't make much difference. So we could, if we wanted, we could add W to this. The reality is that for a wing, the width, this thickness of the wing doesn't make much difference. And so we haven't included it. But the point is, this can be any characteristic length that we want. And then, so finally, what we want to be able to do is we want it to be dynamically similar. Similitude. And that is that we can use some other property. And usually for us, dynamic similitude means that either the Euler number of the model is equal to the Euler number of the prototype, if you want to get lift on a system. And we'll go do a little example in a second just to reiterate that. So this is for, this would be for pipe flow, which is internal flow, or it could be for a wing flow and lift, which is an external flow. You know, in a pipe, you're interested about flowing inside the pipe. You don't care about the fluids on the outside. And the other one would be the Froude numbers, or Froude numbers. I'm never quite sure how to pronounce that. And that is for boats. So with a free surface. So in other words, if you have a water tank and you pull a boat through it, you know, and you measure the forces you have to apply to pull the boat through at a certain speed, then the information that you might want to process is relative to the Froude number. And so these are, very simply, these are the deals. So to reiterate, we know from Buckingham Pi theorem, there should be 3 non-dimensional variables that describe our system because of just the things that we think are important. We could have added W in here. We could have also added gravity, but you realize that for every single term you add extra, you're going to end up with an extra pi group, so you're going to make your system more complicated. So you'd like to boil it down to the bare minimum in terms of the number of variables. So in our system with 6 variables, we know we have at least 3 pi groups. We know that we're going to want the model to be the same in the first place to the prototype in terms of dimensions. So we know that this presumably could be one of the pi groups. We're going to make sure that we match the Reynolds numbers between model and prototype. So we're guessing that this probably is one of the pi groups as well, second one. And if we want to know what the forces are that apply on this, then the other potential pi group is possibly going to be the Euler number. And so we have 3 pi groups. You could do it by Buckingham Pi. Depending on how you choose your primary and secondary variables, you'll get different results. So in a test, typically you'll be say use this as your primary variable just for ease of marking, so that you all get the same result. But you don't have to, it's not preordained. And if you use different variables as your primary variables, say instead of using p equal to these and calculating Buckingham Pi, you'd get a different result of non-dimensional variables than if you used, for instance, viscosity or velocity as your primary variable. They'd all be relatable to each other, but they'd be different. Yeah.
Why do you just gravity?
Because it's acting on, well, because we could use gravity and we'd end up with an extra term. It would just be that that term wouldn't be significant because the results wouldn't vary very much with it. And so I guess what it's saying is that if you look at the flow on the wing, most of the lift that you get is not going from, so if you go from the top of the wing to the bottom of the wing, that distance, I don't know, on an aircraft wing it's probably 10 centimeters. The change in pressure you get for that is trivial, and that's due to gravity, right? Because it's the weight of the air. But the dynamic forces that are applied on the wing by the velocity going past it and providing lift is probably 3 orders, 5 orders of magnitude larger than that pressure. And so I guess what it's saying is that the pressure difference across the wing due to gravity is much smaller than the lift that you get from the velocities around it, and therefore it just doesn't make any difference. So if you did your experiment on the moon versus on this planet, the lift that you get in the same atmosphere would be the same. Yeah. So anyway, so I think that's the rationale. So gravity would add a hydrostatic, wouldn't be hydrostatic in air, right? Hydro is water, but it would add a pressure only with elevation, which is small. And so in the basic deal for you then is that you do an experiment. So it's quite straightforward. So this is it. So the experiment is this. You run this. In the model, you have a velocity in the model. You measure the lift in the model, but the lift is also equivalent to the pressure difference between top and bottom, right? So that's how a wing works. You have P1 on the top, you have P2 on the bottom, and the lift force is equal to P1 minus P2 multiplied by length times span, roughly, right? That's really what we're doing. So let's assume, so typically in a model you'd measure the force, because it's easy. You could measure the pressure, I guess, but you could always convert that force into a pressure difference, which makes it easier. So we'll use that. So you apply a velocity, you measure fluid pressure, and you have those 2 data points. And so what you could do is you could think about then plotting that data point for a particular velocity in terms of this figure, which would be a Reynolds number, which is the velocity you're flying at, the density of the fluid, which is air, times a characteristic dimension of your wing, which is length, divided by the viscosity of the fluid, whatever that is. And so you do your experiment at 1 meter a second, say, and you'd have one data point at this particular Reynolds number. And you think about what the other components would be. Almost certainly it's going to be an Euler number, and the Euler number is defined as a change in pressure. Let's just write it as pressure, not change. So it's this delta, let's write it as delta P divided by a density and a velocity squared. So we haven't said whether this is the model or the prototype velocity, but if we run it at this velocity, maybe we calculate a force is equal to 1 Newton, and we can use that to calculate the actual pressure, right, from this expression here. And so if we know the pressure, if we know the velocity we're flying it at, and we know the density of the fluid, then we have an Euler number that we've taken from our calculation. And so this is for our model and our model. And so that's done. So now we have a prototype. And we can do two things. The first thing, the easiest thing to think about is we run prototype at the same Reynolds number for the prototype, which is equal to the Reynolds number, the Reynolds number for the model. So in other words, if we know we're on this line, then we know that for our prototype, then since this was the behavior of our model at this particular Reynolds number, we're going at the same Reynolds number, we'd expect that the place we are on this graph is exactly that same point, and so this would be the value for the prototype as well. And so if we run it at the same Reynolds number, then we'd expect that the Euler number for the prototype is equal to the Euler number for the model. And so if we write that out in longhand in terms of what the equations are, so the change in pressure that we measure on this thing in the prototype, which we don't know, divided by the density of the fluid in the prototype, the velocity in the prototype squared, has to equal this pressure that we've measured in the model, which we do know, the density in the model, which we know, and the velocity squared in the model that we also know. And so we know everything on the right-hand side. If we know what medium we're flying in, if it's in air, and we've done our experiment in air, then we know the density. And we know the velocity at which we are running our prototype at by scaling these things. Then the only unknown we have is the pressure. So from knowing that, we have this. So that's one way to do it. The alternative way to do it, it's really the same way, but it's different, is we run the experiment and we run it at the velocity equals 0.1 meters a second, 1 meter a second, and 10 meters a second. So if we do that, then our system would now look like this. So we'd have the same Reynolds number plot versus Euler number, and we'd run it at 1 meter, 0.1 meters a second, 1 meter a second, and 10 meters a second. So we'd have a whole bunch of results. We'd measure the forces on the wing at these different magnitudes. We'd have these 3 points. And so this would be, it's a Reynolds number, but this would be 0.1 meters a second, the equivalent Reynolds number, and this would be 10 meters a second. So we'd have these 3 points, and this would be for our length, to span, which is equal, what is it for a wing? I don't really know what it is for a wing. I imagine it's certainly more than 10. So this is for 10, for this particular geometry. So we have these 3 points, and by extrapolation we could think that there's a curve that goes through here. Now if we run our prototype, We run it at a velocity of, I don't know, 5 meters a second. We can use that to calculate the Reynolds number of the prototype, which may be here, say. So Reynolds number of the prototype. And so what we can do is if we just go up to this line here and across here, this would be our Euler number for the prototype. So we run the prototype at some velocity. We do it at the Reynolds number that's appropriate to that velocity. That allows us to calculate the Euler number at that prototype at that particular velocity, which allows us to calculate the pressure, which allows us to calculate the lift force. That's it. So it's an incredibly powerful technique. We've said nothing about differential equations. We've just run an experiment at a particular condition, and we've used that to satisfy a couple of things. Remember, geometric similitude. The model looks like the prototype if you expand it, or the model is typically a shrunk down version of the prototype. I guess they're usually smaller, right? Just because you don't want to have, if you had a wind tunnel the size of a real airplane, then you could just put the real airplane in it. So geometric similitude has to look the same. So the length of the prototype to the span has to be the same in all cases. If you have it, you can run it at a particular Reynolds number. If you have similitude between the Reynolds number of your model and your prototype, you end up with 1 point, and you can get the Euler number, and therefore you can say something about the forces applied on it. If you don't run it at the same Reynolds number, but you run it a span of Reynolds numbers that traverse the range at which you like to know the real behavior of the prototype, then you have a single curve here, which allows you to define behaviors. So irrespective of your Reynolds number, you can always go across here and figure out what this case is. So, well, I guess that's it. That's exactly what experimentation is all about. So you have to satisfy those three conditions. If you only want to run one experiment, and you want to satisfy these three conditions of geometric similitude, kinematic similitude, and dynamic similitude, then you use a model that looks like the real prototype. You run it at the same Reynolds number that you'll run your prototype at, and then directly from that you get the magnitude of the Euler number with 1 point, one experiment. If you want to run more than one experiment, then you could run it at multiple Reynolds numbers, and instead of getting a single point, you get a line. And so this is what the experimental space looks like if you have three variables, right? So we have the variables a Reynolds number, we have Euler number, and we have a geometric parameter here. If we had, what's it going to be? Maybe if we used a length to diameter of 5, to see if the pressure, span, I keep on saying span, maybe if it was equal to 5, and you did it for a different shaped wing, then you'd get a different curve. And so if you look at only, if you had two variables, then you'd have just a single line. So in other words, if you only had one geometry that you're dealing with, then you'd have a single line in Euler number and Reynolds number space. If you had a variety of different geometries that you're dealing with, then you'd end up with a whole bunch of curves in this space as well. And so depending on the number of variables you have, the results of your experiments and how you'd map them would change according to this. And so I don't want to rush in this, but I think that's kind of illustrated in here. This is Buckingham pi, which you'll have looked at. But this is basically the idea here, right? So if you have 2 pi terms, then you can imagine that in our particular case, for a particular length over diameter component, if the geometry was the same, you'd end up with one curve only. And this happens to be Reynolds number, and this happens to be Euler numbers. We've done it. If you ended up, in our case, we have 3 variables. We have Reynolds number, we have Euler number, and we have length over diameter. Then we'd end up with this for different numbers of length over diameter. Length over span is equal to 1, length over span is equal to 10, length over span is equal to 100, or whatever it would be. And so you could map this out in this space. So what it's saying is that any time you wanted for that same geometry to calculate what the lift was on that system, then you just choose the appropriate Reynolds number that you're running, you want to fly your plane at. You find what the geometry is that you come up against, and you get an appropriate Euler number, for our case on this line, and you can calculate the uplift. When we deal with internal flows, obviously a flow around a wing is an external flow. When we deal with internal flows, we can basically use the same idea to be able to understand how it works for that internal flow. So in other words, we've taken a wing that looks like this. These are my parting shots. A wing that looks like this, and we get flow around it. And we're interested in the forces that get applied to this wing as a matter of lift. If, for instance, you took a pipe and closed off the ends, you could also look at flow around the outside. In this particular case, there probably wouldn't be much lift attached to it, but you could do that. But you could also take a pipe where you flow stuff instead of on the outside of it, which isn't really the use of a pipe, but we look at flow on the inside. And what we would know is that to drive flow along that pipe between the upstream and the downstream pressures, there's some difference in pressures we'd have as we go from upstream to downstream. We're using energy if we're having to work against viscosity. And so in the same way that we've talked about a Reynolds number that classifies the behavior of the flow around this wing, we could also write a Reynolds number that classifies flow velocity in this pipe. Yeah, I will use D. And so in our particular case, a velocity, a density of the fluid, a characteristic dimension, and viscosity would give us a Reynolds number of flow in the pipe. And if we measure the pressure drop between upstream and downstream, then we could also use an Euler number, which is equal to the difference between the upstream and downstream pressures, the density of the fluid, and the velocity of the fluid. And so it'll turn out that when we look at internal flows as well, it's exactly the same thing we're interested in. We're now not really interested so much in the force that's put on the structure to be able to lift this wing, but we're interested in the pressure difference between the upstream and downstream, which, by the way, of course, you know from conservation of momentum, will give you a net force that you have to act against to be able to hold that pipe static. But we're interested more in the horsepower that we have to apply to be able to push fluid through here. And so it's just a different viewpoint, I guess, in looking at the pressure difference between upstream and downstream, but it's no different from being an Euler number. And so in the next session, what we'll deal with is we'll talk about fluid flow in pipes, and we'll start using the same kind of ideas to be able to look at what the fluid pressure losses are and to be able to characterize behavior in pipes. So I think that's the summary.